finish with the line integral. Find work done. Moving the object from 1, -2, 1 to 3, 1, 4 through the given force field. So notice here they didn't tell us how we're getting from point A to point B, right? They didn't specify an actual path. Let's check to see if this force field is conservative. Because if it is, then the path doesn't matter, right? It's path independent. How do you determine if the force field is conservative? Here's the test. Conservative vector fields. Find the curl. Curl 0. This means that F is conservative. That means we have a scalar function whose gradient is the vector field. That's where we're at. Let's find the antiderivative of v sub z with respect to z. Xz cubed plus some function of x and y. Take its partial with respect to y. Just doing x for some reason. We know that has to be equal to x squared. And our function has to be the antiderivative with respect to y. So here's where we're at right now. Now take its antiderivative, take its partial with respect to x. Now it's going to have to equal what v sub x is. G prime of x is 0. G of x is just some real number. Take that as your potential function. And that is work. But we just showed that vector field is conservative. We can use the fundamental theorem of line integrals. The integral is path independent. All that matters is the end point and the starting point. There's our V. You valued that at 314. It's 4 cubed times 3. What was it? What is 3 squared? $64 times 3 is not 92. 192, sorry. And then add that to 9 to a 196. Now 1, negative 2, 1. Oh, that first one's easy. And that's 1 times negative 2. So 1 minus 2, negative 1. And there's your work. So remember how curl is defined? Set of cross products. Partial x, partial y, partial z is your applet. So just what, partial y minus partial z. Partial z minus partial x, and then partial y minus partial x minus partial y. Let be conservative vector field such that F equals negative del V. Particle constant mass m moves through F from point A to point B. I want to prove V of A plus half m V sub A squared equals V of B plus a half m V sub B squared. VA and VB are just the magnitudes of the velocities of the particle at point A and point B respectively. Start with Newton's second law. F has to be m times A. If we take a look at the derivative of V squared with respect to T, magnitude of V all squared would just be V dot B. Use the product rule. What is the derivative of V though with respect to T? What is it? Yeah, derivative of V with respect to T as well. It's acceleration, right? That since the dot product is commutative, they're actually the same. So we can write that as 2 times v dot a. So if you look at v dot a, that's just a half d dt of v squared, and that's going to be important. Work is that line integral. We said f is ma. But dr v dt. So I should write this. And factor out the m. Rearrange, you're left with v dot a dt. But we just said v dot a is a half d dt of v squared. Fundamental theorem of calculus, part 1. Antiderivative of d dt v squared. dt is just v squared. And derivatives and antiderivative, that's how they're related. Then part 2, we evaluate that from t equals a to b. Velocity at time b was v sub b. Velocity at time a, v sub a. There's the work, a half m v sub b squared minus a half m v sub a squared. On the other hand, f is negative del v. Means F is conservative. The only thing that matters is the starting point and the end point. Work would then be V of A minus V of B. But both of those expressions we just found, right? Have to be the same. So since 1 and 2 are both expressions for the work, we must have them being equal. Rearrange your terms. As desired. What is that? 1/2 mv squared, what does that represent? For what energy? It's just kinetic energy. I'm going to represent it as K sub E. V is potential energy. That means this here would be what? Kinetic energy plus potential energy at point B. Kinetic energy plus potential energy at point A. And that says they're the same. That's conservation of energy. Energy is conserved in a conservative force field. Stop there. I'm going to let you work on that on your own. Has to do with the conservative gravitational field. Surface integrals are the last type of integral that we study. And so we did the line integral, the path integral, right? So we integrate over some path. Surface integral, we're integrating over a surface. Means we now have to deal with parameterized surfaces. And so we say G is a parameterization of the surface S with the domain of D. Assume that G is continuously differentiable, one-to-one, and regular, except at the boundary of D. Right, then integral, double integral sub S, f ds is called a surface integral. Specifically, we're integrating f along the surface of S. Notice our differential. It's not an area differential, it's a surface differential. Evaluating the surface integral, you set it up as a double integral over the domain of your parameterization D of f evaluated along G, right, your parameterization of the surface, times the norm of the normal vector to the surface, dA. Right, and normal vector, G sub U cross G sub V, or G sub V cross G sub U, depends on the orientation. taking the surface integral of a vector field. We call this a flux integral. Right? The value of the integral is called the flux of the vector field through the surface. Evaluating flux, you're integrating over the domain. Evaluate F, your vector field along G. Dot it with your normal vector, dA. Again, and typically GU cross GV or GV cross GU, depending on orientation. This is where orientation of your surface matters. How so? Because that determines on how n is pointing. Remember, you have two types of normal vectors. They are either going to point away from the surface or into the surface. So the orientation of the surface is either outward pointing or inward pointing. Unfortunately, you don't know what order you want until you actually calculate it. And so typically what we'll do is we'll just calculate G sub u cross G sub v and then determine if that's the proper orientation of the vector. If not, we'll just multiply by minus 1. And of course, notice for the scalar, it doesn't matter. When you take the normal vector, it's regardless of which direction it's pointing, it's the same. So the orientation of the surface here really doesn't matter, but it does for flux. Your first exposure to flux probably wasn't this course. It should have been Intro to E&M, where you studied electric flux and magnetic flux. Any vector field has a flux. So you can even think of like it's essentially a flow rate. And what's the net flow of the field through the surface? So you can even use flux in terms of water flow through a specific surface. Obviously, there's gravitational flux as well. And so we're now just extending it. But let's start with some scalar surface integrals. We'll eventually work our way up to flux. Probably tomorrow. Once we evaluate z along the surface of the cylinder, y squared plus z squared equals 4, for z greater than 0, and x between 1 and 4. The video on surface integrals goes over, is it 3, maybe 4 surfaces that it tells you how to parameterize the surface, as well as the normal vector for that surface. One of the surfaces is more of the category of surface. And it's a surface that can be written in the form z equals f of xy, which this one can. Then the surface would have the parameterization x, y, and then your function. The key here is the fact that we're told z is not negative. That's why it's only the positive square root, right? We need a domain. Well, they already told us x. What about y? Greater than or equal to 2. That would be infinite. That'd be a problem. -2 to positive. It's one of the known forms. So the derivations through the videos. So I'd go watch that. But if you can write it in the form z equals a function of x and y, then that's your parameterization. X, y, and then the actual function itself. Normal vector, which I actually don't care about. I just care about the norm of the normal. Again, there's a derivation in the video. I'm not going to go through it again. square root of 1 plus the partial of your function with respect to x squared. Well, the function purely of y, so that derivative is 0. Plus the derivative of your function with respect to y squared. So take the partial of root 4 minus y squared with respect to y and then square it. We can simplify that. Write it as a single fraction. 4 minus y squared plus y squared is just 4, right? All over 4 minus y squared. Square root of 4 is 2. There's our norm. Keep in mind, of course, this means that the surface differential is that. And it's norm of the normal vector of dA. So we can take the double integral over d, evaluate your integrand along g. Well, the integrand is just z, isn't it? The integrand becomes just the square root of 4 minus y squared. Or 4 minus y squared, rather, square root of that. Then times your ds, which became that 2 over root 4 minus y squared dA. And notice how this simplifies. Two times the integral over d dA. So that's just an area integral, isn't it? What's the area of our domain? It's the area of the domain. Remember, our domain is D. And what was D? What kind of region is that? X goes 1 to 4, y goes -2 to +2. What kind of region is that if you were to draw that out?
Circle. Cylinder.
What region? What kind of region is that? What's the area of a rectangle? So what's the area of our domain? Actually, I did it wrong. That was the x-axis, so I should have gone all the way down. There. Area is 12. So you want to integrate x squared over the surface of the unit sphere. Parameterization of a sphere, cosine theta, or of a sphere is the radius, cosine theta sine phi, the radius, sine theta sine phi, and the radius, cosine phi. Unit of sphere means radius of 1. We're the entire sphere. Theta goes 0 to pi, phi goes 0 to pi. Norm of our normal vector is the radius squared times sine of phi.
What is our radius?
It's a unit sphere. Radius is 1. We're going to be integrating over our domain. X squared cosine squared theta sine squared phi then it's going to be times sine of phi dA. Set that up as an iterated integral. Cosine squared theta sine cubed phi is the integrand. We're integrating 0 to pi, 0 pi d phi d theta. Just plug that into a calculator. We should get 4 pi over 3. It's not terrible to do by hand, but we're dealing with part of a sphere, so we're going to use the parameterization of a sphere. Here. It's the upper hemisphere. Theta still goes 0 to 2 pi. But phi only goes 0 pi over 2. Of course, the normal vector A squared sine of phi. Z squared would become A squared cosine squared of phi, then times A squared sine of phi dA. I'm sorry, not plotting. And then set up your iterated integral. A to the fourth times the integral 0 to 2 pi of the integral 0 to pi over 2, cosine squared phi times sine phi d phi d theta. Again, that is not a terrible integral to do. You should get 2/3 pi 8 to the fourth. And the important part is getting the setup. That's generally the hardest part. I'm gonna let you look through that at home. Because on Friday, I'm going to start with flux. So I'll start here tomorrow. Do is now stop the recordings.